Ever wondered why chemistry seems to have its own language? Why does naming complex ions and coordination complexes sound like a secret code? Well, let's unravel this mystery together. Just like a name can tell you a lot about a person, the name of a chemical compound can tell you a lot about its structure and properties. And when it comes to complex ions and coordination complexes, it gets even more interesting. These compounds consist of a central metal atom or ion, surrounded by molecules or ions called ligands. The way we name these compounds gives us a clear picture of what's going on at the atomic level. Now you might be wondering, why is this important? Well, imagine trying to assemble a piece of furniture without knowing what the parts are called. You're given a bag of screws, bolts, and washers, but the instructions just refer to them as those metal thingies. It would be quite a challenge, wouldn't it? Similarly, understanding the names of complex ions and coordination complexes allows scientists to visualize their structures and predict how they will interact with other compounds. So how do we name these complex ions and coordination complexes? The process involves several steps, starting with naming the ligands, which are the molecules or ions surrounding the metal. Then, we name the metal atom or ion. The names of the ligands and the metal can give us clues about their charges, the number of ligands, and the overall charge of the complex. And there's a twist. Depending on whether the complex ion is positively or negatively charged, we might add an 8 to the end of the metal's name. It's like the metal's way of telling us, hey, I'm part of a negatively charged complex. So, are you ready to dive deeper into the fascinating world of complex ions and coordination complexes? Stay tuned to find out how to crack this chemical code. Let's start our journey into the world of complex ions and coordination complexes. Imagine them as a bustling city, where each skyscraper is a unique complex, with its central metal atom acting as the foundation and ligands as the building blocks. To decode the name of each skyscraper or complex, you must identify 3 key elements: the central atom, the ligands, and the charge of the complex. The central atom is the heart of the complex, usually a transition metal. Ligands, on the other hand, are molecules or ions that donate a pair of electrons to the central atom to form a bond. They are like the loyal citizens of our skyscraper city, always supporting and surrounding the central atom. Let's talk about the charge of the complex. It's like the reputation of each skyscraper in our city, whether it's popular, positive, infamous, negative, or neutral. You determine it by adding up the charges of the central atom and all the ligands. The naming process starts with the ligands. Anionic ligands change their ending to O, like chloride becoming chlorido. Neutral ligands often have special names like H2O becoming aqua. If there's more than one type of a ligand, we use Greek prefixes like di, tri, tetra, and so forth. Next, we name the central atom. If the complex is positive or neutral, the metal keeps its name. But if the complex is negative, we add 8 to the metal's name. For instance, cobalt becomes cobaltate. Remember, ligands are named first, and then the central atom. And when listing ligands, we ignore the prefixes for the alphabetical order. So let's say we have 3+. NH3 is a neutral ligand named amine, and there are 6 of them, hence hexamine. The metal is EaCO3+, so we use cobalt 3. Putting it all together, we get hexaminecobalt the 3. With these basic rules in mind, you can now start to understand the language of chemistry. Now that we have the basics down, let's apply this knowledge to some real-life examples. Let's start with our first complex ion, 3+. Here, NH3 is neutral and named amine. We can see that there are 6 amine ligands surrounding the cobalt ion. We know that the metal is Co3+, because when we add up the charges, we get a positive 3. This complex is positive, so we use the name cobalt the 3, not cobaltate 3. So the name of this complex ion is hexaminecobalt the 3. Next, let's take a look at Cl3. The chloride anions in this case are counterions, not ligands. Therefore, the name of this complex ion is hexaminecobalt the 3 chloride. Moving on to K2, we see that the K+ cations are counterions. There are 4 CN ligands, named cyanido. The metal is Pt2+, because when we add up the charges, we get 0. Here, the complex is negative, so we add 8 to the metal name. As such, this coordination complex is called potassium tetracyanidoplatinaate 2. Our last example for today is Bar, the H2O named aqua, and Cl, named chlorido, are ligands, while Br is a counterion. The metal is Q2+, because when we sum the charges, we get 0. This complex is positive, so we don't add 8 to the metal name. Listing the ligands in alphabetical order, ignoring the prefixes, we get the name triaqua-chlorido-copper 2-bromide. Remember that the overall charge of a complex ion is the sum of the charge of the metal ion and the charges of all the ligands. The names of the ionic compounds include a name for the cation and a name for the anion. And to name a complex cation or anion, you must be able to determine the oxidation state of the metal. See, it's not that complex after all. Mastering the naming system of complex ions and coordination complexes is no small feat. This system is a beautiful blend of rules and conventions, which, when understood, can reveal the structure of these compounds. We learned that the names of these compounds include a name for the cation and anion, and that determining the oxidation state of the metal is crucial. We dissected how the overall charge of a complex ion is the sum of the charge of the metal ion and the charges of all the ligands. We also delved into the systematic naming rules, starting with naming the ligands first, then listing them alphabetically. We noted that the metal is named last, and if the complex is negative, the metal name ends in "ate." This journey through the nomenclature of complex ions and coordination complexes has been a thrilling one. Remember, practice makes perfect. Keep practicing and you'll be fluent in the language of chemistry in no time.